Okay. All right, can you guys see that okay?
Yeah, I can see that.
Okay. I will try and write as best as I can so you can read my writing. I'll try not to write too small either. Okay. Well, since there's only 4 of you here, we can kind of bounce around just a little bit to see, what questions you guys have. So do you have any that you want to ask just kind of right off the bat? Something that's just been like, why is that the way it is?
Um,
There you go.
so basically, I guess it's for this in this. You can hear me just fine, right?
Yep.
Okay, good. So for this last section, 3.1, we're finding derivatives, and I think the first example that we did in the notes, the first example, we were finding the slope of the tangent line. That's example 1, and we got a number, and it was -3, and that's kind of uncommon, right? Because
in their public school system than another. In the short term, that may not seem like a big deal, but if
anyways, so getting a number is kind of non-standard, correct? Like as far as most problems that we're going to be given.
If it just wants the derivative, yes. If it wants the slope, then no, you should pretty much always come out with a number. The only time you'd have like another letter in there is if that letter was defined to be a constant.
Gotcha. So in this case, we were finding the slope of the tangent line at a given point, but sometimes I think we're asked to find the derivative and it's not at a given point, and in those cases we end up with an equation, right?
Yeah, you'd end up with a function. The one exception is if the function itself is linear, then the derivative will come out as a value every single time.
Right. And so when it's not linear, say it's like quadratic, then we come out, you would say the derivative is a function, right?
Yeah. Mm-hmm.
And then we could use that function to find the slope of a tangent line to any x in that original equation, right? In that original function, right?
Yeah. Mm-hmm.
Okay.
Yeah, and you would just plug in whatever that x value is straight into the derivative, and then that would give you the slope.
Okay, thanks. That's pretty fancy. Yeah.
Yeah, it is pretty nifty. And that will be like derivatives will be a topic that you'll see in your entire calculus journey. If you're going on to any sort of engineering or science major, you'll see it in physics. You might even see it in chemistry, depending on how high you would go with that. If you're a business major, you'll see it in business applications. So derivatives, derivatives are used a lot. They're used pretty much everywhere.
Yeah, it's funny because I told my dad I'm going to be taking calculus, and he's like, "Oh, calculus is going to be really useful," and I was like, "I thought like trigonometry was the most useful math class I've taken because you can like use it to figure out how to build stuff and whatever." And he's like, "However useful you think trigonometry is, calculus is like on another level." So yeah. Well, thank you.
Sure. Okay, so I'm glad you asked that question, actually. So section 3.1, it is on the exam. But you have to keep in mind that chapter 2 is also on the exam. So mostly of the exam is going to be on chapter 2 because that was the bulk of the material that you guys have gone through. So 3.1, it is on there, but it's not going to be on there a lot. Most of it is off of chapter 2. So that's going to be on, your limits, being able to evaluate a limit with a table, being able to evaluate with the graph, evaluating algebraically, like if you're given the function, can you manipulate it until you're able to plug in the value, that sort of thing. There'll be questions on continuity. Let's see what else. One-sided limits, limits that are unbounded, so limits that will go off to infinity or negative infinity. So the bulk of it is going to be on chapter 2. Oh, also like the epsilon delta proofs. Let's see, what else can I think of? That should do it. So a lot of people want to know, is like, okay, well, how do I study? The best way to study for math is to actually do the math. And when I say do the math, I mean like actually write out and do the problems. If you just read the material and if you just look at something and go, okay, yeah, I know how to do that, and then you skip over it, that's a bad way to study. Because what happens is that you might get that same question on the exam, and then you're like, oh, wait, I don't know how to do this. So what you want to do is when you're doing the problems, prove to yourself that you can do it. Don't just assume that you can. Prove it that you can actually do the problem. So a good thing to use is the study guide. It's on the modules page. If you can do the study guide, you should be pretty well off for the exam. Now, I know some of you, what you just heard was, if I memorize the study guide, I can do the exam. That's not what I said. If you can do the study guide and the problems and you can really understand them, oops, where'd that go? Then you can do the exam. Not sure why that turned off. Get that back. There we go.
I have one more kind of question, Professor.
Yeah.
So on these like past 2 quizzes, I've been going, well, I went right up to the time limit for the first one, and I took almost the whole time, I think like about 40 minutes on the second one. And, normally when I take tests, I'm kind of quick, but it seems like I need more time than I expected on these. And I was just wondering, like, could you just like say, like, is the test going to be pretty similar, like a similar time allotment per problem as the quizzes?
It's like there's 3 hours for the exam, and there are 22 questions. So it's like yes and no. Some of the exam questions will be quick because the way it's broken down, there's like a multiple choice section. Then there's also a fill in the blank section as well as a free response section. So the multiple choice section, those are designed to go a little bit quicker anyway, as well as kind of like the free response, or I'm sorry, the fill in the blank. The free response is where you'll have questions that'll take a little bit more time because they might be a little bit trickier. So you kind of have to sit there and think about it for a minute.
Yeah. Okay. Yeah.
But I haven't had anyone really say, I ran out of time on the exam. Or if they did, they never said it. And that was true even in person. The quizzes were always more of a time crunch. And the exams were not so much.
Well, that's good.
Because of the
Yeah.
students.
Yeah, I think on the quizzes, for a couple of those problems, yeah, sometimes I was a little bit surprised by little bit of curveballs, and I think I was just getting nervous and kind of going slow. So hopefully
Yeah.
I'll be okay. Okay.
It gets better, especially quiz 1. That's always the worst, because it's like, oh gosh, I'm taking an online calculus exam or quiz. It's the first time I'm doing this, and so there's a lot of nervousness going along with that first quiz, and then even for the first exam. But then everything after that, it's usually pretty okay.
Definitely.
Okay. All right, so we have a lot of people in here. So since there's a lot of you, it's not really going to be the best idea to just take questions one by one, because then you're going to be sitting there for a long time before I get to you. So I think what I'll do to start is just kind of do like a general review, kind of like an overview. And then if you guys have questions in there about like what we're doing, you can feel free to ask it. And then towards the end, we can start getting into more specific things that you want to know about. Okay, so first off, let's go over limits with a graph, because there was I think there's a little bit of confusion on some of those problems based on the first quiz. So let's take a function. Okay, let's stick in some values. And let's do there. Okay, so piecewise function, those x values, those y values. So we're going to use this graph, and we're going to call this f of x. We're going to use it to just evaluate a bunch of stuff. So limit values and also function values. Okay, so let's start out with this one. Let's say the limit as x approaches 10 from the left. So I think what some people wanted to do is they were trying to come up with like what the function actually was. And you can totally do that if you want to, but I would only recommend doing that if you had a lot of time, because that's coming up with a function for this is going to be a little time consuming. So instead, you just want to use the graph. So the whole point of it is to figure out, okay, well, if you were tracing along the curve, what y value would you get, or would it look like you would get as you got closer and closer to this x value? So we're approaching 10 from the left side, so that means we're coming in from over here, and you're just tracing the curve. And if you have to jump over something, you jump over it. If you have to cross a gap, you just cross over until you get to whatever number this is. Like, don't stop tracing until you reach that 10. So if we traced in and we get to that -10, what y value did you just stop at?
0.
0. So that would be your answer for the limit. And it's nice because you didn't have to come up with the function yourself, nor did you have to plug anything in and calculate it. You just had to look at it and trace. Okay, so if you're tracing, oops, there should have been negative 10s in there. If you're tracing from to get to negative 10 from the right, the right side is, coming in over here. Some people, they would trace down this curve and then they stop because they're like, well, how do I get over to there? It's like, well, just keep tracing. If you have to jump over, just keep jumping over until you get to that negative 10. So when we trace over to the right and got to negative 10, what y value does it look like you would land on?
Zero.
Yep. So that's kind of cool when that happens, when your left side and your right side agree like that. You got the same value. What does that imply, or what does that actually tell you?
That the limit does exist.
But which one? Like the limit of f of x.
The limit at x equals or as x goes to negative 10.
Yeah. So not only does it exist, but you also know the value of it. And it would have to be the same values you got before, which would have been 0. So if the left limit and the right limit agree, you know that the overall, the two-sided limit is going to exist, and it's the same answer. Okay, so let's look at actually one more. What's f of negative 10? So we're switching gears just a little bit. So the limit value, now we want the function value.
So that's also 0.
Yeah. So when it's asking for the function value, it's all it's really saying is like, okay, when x is actually negative 10, what's the y value that goes with it? So in that case, it is also 0. So here you have the function value is the same as the limit value, but that is not always true. Sometimes they're different. Okay, does anybody have any questions on A, B, C, or D? Okay, let's move on then. Let's take the limit as x approaches negative 5 from the left. We'll take it from the right. And then the two-sided limit. And then we'll do the function value at negative 5. Okay, so go ahead and try those. Don't say anything out loud just yet. Everybody has a different processor speed. And we're using the same graph as before. All right. So the limit of f of x is x approaches -5 from the left. What do you think that answer is? Like what y value does it look like you would approach as x approaches -5 coming in from that left side?
Would that be 0?
Yeah, it's going to be 0. Even though there's a hole there, it's like you don't care. You don't care if it's a hole, if it's a point. You know, it's all about what is it approaching, not where is the actual point. And some people kind of get that confused or a little jumbled together. So you're still just tracing in to -5 from the left side. And once you get to -5, you stop and you look and go, all right, what does it look like I'm just about to run into? Y equals 0. All right, now when you trace into -5 from the right side, you know, again, you're tracing over until you get to -5. And it looks like you're going to run into y equals
-4.
-4. Okay, so now we have a case where the left limit does not equal the right limit. So what does that tell you?
That the limit as x approaches -5 does not exist.
It does not exist. For all you Lindsay Lohan fans out there, that is what she was talking about in that movie Mean Girls. Okay, and then finally, f of -5. So the function value, when x is -5, the function value is
Wouldn't that still be -4 because of the
Yeah.
closed circle?
Yep. Yeah, now you are looking for where the point is. So now it does matter if it's open or if it's closed. So you do want that closed point. Okay, any questions on E, F, G, or H? And if you have a question, you're gonna have to ask it out loud too. So while I'm screen sharing, I can't really see the chat. Okay, let's go on. Let's do the limit as x approaches 10, positive 10 from the left. The limit as x approaches positive 10 from the right. The overall limit. And then just for fun, because I drew it in there, the limit as x approaches 5. Okay, so as the limit approaches of f of x as x approaches 10 from the left. So you're tracing in. Now it's on this piece right here. Where's it going?
Positive infinity.
Positive infinity. So yeah, if it's hugging a vertical asymptote, it's gonna go off to either positive infinity or negative. So the negative infinity, that's gonna be for the next one, because now it's shooting down. So does your left and right limits agree? Like, are they the same?
No,
Nope.
so they don't exist.
So they
Or
don't
it doesn't
exist.
exist.
Yeah. Yeah, anytime you have two different answers for the left and right limit, the two-sided limit automatically does not exist. Okay, and then this last one, the limit is x approaches 5.
Eight, because it's a closed circle up there.
That would actually be f of 5. So the function value is 5 because that's where the point is, but not the limit value.
Oh, so that doesn't exist?
It does not exist. And why does it not exist?
Because they have different values.
Yeah,
From the left and the right.
yeah, exactly. The left side approaches 4. The right side approaches -3. So they're different. They don't like actually meet or look like they connect together. So the limit does not exist. Let's do one more just for practice. What's f of 10?
Undefined.
Yeah. That does not exist as well. How do you know that?
There's a big dotted line in the way.
Yeah, that's where the vertical asymptote is. So if you got a vertical asymptote or just a hole and no point above or below it, then that's undefined or it does not exist. All right, any questions on, oops, on these? Second, if you have one, feel free to ask it. It's like, don't just sit there and wonder. Okay. You're good. All right, let's see. Let's go ahead and talk about continuity. So somebody describe what it means for a function to be continuous as if you were talking to someone that is not in calculus. Like if you just walked up to somebody on the street and because they asked you, what does continuity mean? Like, what would you tell them?
So I would say a continuous function is one that you can draw on a graph without picking up your pencil.
Yeah. That is the easiest and best way to explain it. Okay, so that is like the layman's way to explain it. But of course, because you're in calculus, there is a formal definition to it, and it's what they prove or what they use to prove that something is actually continuous or not. So for the formal definition, there were 3 things that needed to happen or that needed to occur. What was one of them?
F of C is defined.
Okay, and what does that mean?
It exists.
Yep, it exists. So if you're looking at the graph, like what would have to be there?
A line or a dot.
Yeah, you'd have to have some point at that f of c. If there's a hole or a Verglass asymptote or something like that, then it's not defined. Okay, so that's the first hurdle. The function has to be defined at c. What's another one?
The limit as x approaches c of f of x exists.
Okay. And what's the third one?
So the limit of f of x as x approaches c is equal to f of c.
Yeah. So the function exists, the limit exists, and that's not enough. The third one says, okay, well, not only do they have to exist, but they have to equal each other. So why is the third one important? Why can't they just, why is it not enough just to have the first two?
So if f of c equaled something else other than the limit as x approaches c, that might look like on a graph, where the limit kind of comes towards one value, and then there's a hole, and f of c, the y value at that x is actually something else, which means you can't draw the function without picking up your pencil.
Yeah, exactly. Yeah, because if they don't agree with each other, that means your function value is either higher or lower than the limit value. And he's exactly right. You just had to pick your pencil up to draw that curve. So it destroys the continuity if these things are not equal to each other. Okay. Any questions on just what continuity is or this formal definition? So continuity is, it's not something that's hard to understand like what it is, but sometimes it gets a little bogged down in this definition part. And the other place where it gets a little tricky is when you start talking about discontinuity. Because discontinuity that occurs in two, or you can classify it in one of two ways. So what are the two classifications for discontinuity?
Removable and non-removable.
Yeah. And when you start to classify them, this is pretty much going to occur when you're given the actual function, not so much when you're given a graph like this, because if you're given a graph, you can identify where the points of discontinuity are, but you can't really classify that easily because you don't know what the function is. So if you have the function, then you can classify it, but if you just have the graph, then you can't. So on these two, the removable and non-removable, like what does it mean if you're removable?
You can cancel it like from the equation.
Okay. Let's define it this way. So like your discontinuity canceled out. So that's usually when you've got like something in the denominator that's making it 0, like whatever that bad piece is, that discontinuity right there is what canceled out. And so you removed it from the actual function. So then for non-removable, how would you define that one?
You can't remove the discontinuity.
Yeah. Okay, so let's take a couple of different functions. And we're going to discuss the continuity of the function. Okay, so let's just take some, or a couple that are a little bit more simple. Let's do f of x is equal to x squared minus 8. So when it says to discuss the continuity, that means you're identifying where the function is continuous, identifying where the discontinuities are, and if it's a removable discontinuity or if it's non-removable. So there's a lot that can happen in that in that little sentence. So what would you say for x squared minus 8? What would you put down? Where is it continuous, and list out your discontinuities?
Everywhere continuous.
Okay, yep, everywhere continuous. Continuous on negative infinity to infinity. So with this one, there are no points of discontinuity. Is that true for every polynomial?
Yeah.
Yep. So if you have any type of polynomial, whether it's linear, constant, quadratic, cubic, quartic, a 10th power, it doesn't matter. If it's a polynomial, it is continuous everywhere. All right, what if you had f of x is equal to cosine?
Well, same thing. It's continuous everywhere.
Yep. Yeah, and there's with cosine. Sorry. Oh, cosine. There are no holes, jumps, skips, vertical asymptotes in the graph. So it's continuous everywhere. Sine would be the same thing. But the other 4 trig functions, so like tangent, cotangent, secant, and cosecant, they are not everywhere continuous because they have vertical asymptotes in them. So some of the trig functions are not continuous everywhere. And most of the rational functions are not continuous either. So like g of x is equal to 3 over x minus 3. So sometimes when it's asking about the continuity, you can also think of the, trying to find the domain, because they do kind of go hand in hand. So like if you look at this function here, what's the one number you cannot use for x?
You can't use 3.
You can't use 3, so you got to leave 3 out of your domain, or you have to leave 3 out of your continuity. So it's continuous from negative infinity to 3. And then 3 to infinity. So now because it's not continuous everywhere, there is a place of discontinuity. So now you're listing out every value that would make that denominator 0. So for this one, that was your 3. And because you have the actual function, now you can classify it as removable or non-removable. So this function right here, like, does it simplify? Does anything cancel out? Or are you just stuck with it?
Looks like you're stuck with it.
You're stuck with it. You can't do anything to cancel, so you couldn't remove anything out of the fraction. So it's non-removable.
Professor?
Mm-hmm.
So a rational function just means like a function that's a fraction, right?
A function that has a function on top and another function underneath.
Okay. Would
Um,
for example, like x over 3, would that qualify as like a rational function?
That would more qualify as that's just linear. So typically your rational functions are going to have like some sort of an x down in that denominator. Otherwise, it would just fall into another category.
Okay, thanks.
Yeah. All right, let's try a couple of other ones. Let's go f of x is equal to x squared minus 7x plus 10 over x squared plus x minus 30. So here you've got another rational function. But before you really start talking about the continuity, what should you do?
You should factor.
Yep, factor it out. So the top, that would just factor into
X minus 5 times X minus 2.
okay. And the denominator?
X plus 6 times X minus 5.
Okay. Now, once you've factored it, go ahead and get your discontinuity going. And then once you have this down, then you can start to simplify it and go from there. But your continuity, you just want to make sure that you're always getting it from the original function, not the one that's simplified. So for this function, like what makes that denominator 0?
Is that -6 and 5?
Yeah, -6 and 5. So we just want to leave those out of the continuity. So negative infinity to -6 and -6 to 5 and 5 to infinity. So then your discontinuity, those are going to be all the values that you just skipped over, or the values that make the denominator 0. So x equals -6 and x is equal to 5. So once you get all that listed out, then go back to your original function or where it's factored, and then you can start to cancel anything if you can cancel. So with this one, you can cancel out your x minus 5s. And before I write the new one, which one of these two discontinuities did you just remove? The -6 or the 5?
The 5.
The 5. So that is your removable discontinuity. This -6, it is still making that function not continuous. So it's still a point of discontinuity. You just couldn't remove it. But the 5, that just disappeared. It's still a discontinuity, but that's since it disappeared, that's why it's called removable. All right, any questions on this one? All right, let me give you one more. Let's do 4 all over x squared plus 1. So think about that one for a little bit. Don't say anything out loud just yet. Okay, now that you've thought about it for a little bit, is this true? Is this function continuous from -infinity to -1, and -1 to 1, and 1 to infinity?
No.
No.
It is not. Okay, so why not? Because I know some of you thought it was.
Because when the -1 is squared, it becomes positive.
Yeah. So x squared plus 1, that doesn't factor. And the trap that some people fall into is they want to say, oh, it factors into this. Or it factors into this, and neither one of them works. So if you have a square plus just a number, that never factors out, at least not over the reals. It'll factor over the complex numbers, but we are not dealing with imaginary numbers in this class. That would be like calculus 4, if you ever go that high. But we are working with real numbers specifically. So if it doesn't factor, you've got a square plus a number, that denominator is never going to be 0. So that thing is continuous everywhere. You can plug any number you want into X, and that is never going to make that denominator 0. So there's no discontinuity either.
So could we go over a problem like number 7 that was on the study guide? It has to do with continuity as well.
The final values of A and C,
Yeah,
that one, sure.
yeah.
Okay, so it was final values of A and C that make the function continuous everywhere. And it was a piecewise function. So AX minus C when X is less than or equal to -1. 2x squared plus 3ax -1 is less than X, which is less than or equal to 1. And then 4 when X is greater than 1. So if this function is going to be continuous, what needs to happen like between this first piece and this second piece if you actually graphed it?
They need to all match up.
What do you mean by that?
Well, so each piece, their endpoints would be the same y value. So you'd be able to draw the whole thing without picking up your pencil.
Nice, exactly. So the pieces themselves like have to connect together. If they don't, then it's not going to be continuous. Like you'd have different y values. So there'd be some sort of a gap where you'd have to pick up your pencil. So he's right. Where one piece stops, the next piece has to pick right up and keep going. So that means if you plugged in -1 into both pieces, what should happen?
You get the same y value.
Yeah, they have to have the same result, so they'd have to equal each other. So you just have to do exactly that, even if it comes out weird. So plug in the -1, and for X, not all the letters, just the X's. So that'd be -A minus C. And then it has to equal when you plug in -1 into the second function. So that would be 2 minus 3a plus c. Now I know some of you are going to be really concerned, like, oh gosh, this one has the equal bar, but that one doesn't. And then you're stuck. It's like, don't get stuck on that. You don't care if there's an equal bar or not. They have to give you the same result. So like the equal bar just means that there would be a solid point, and no equal bar means there would be a hole. You still want the hole and the solid point to be at the same place. So that's why you're plugging -1 into both of these functions. So you still have an A and a C in there. So you can't, get a value for A and you can't get a value for C just yet. So what I would do is move the A's and C's all over to the same side. And right or left doesn't really matter. So if we brought everything over to the left side, that'd be 2A minus 2C is equal to 2. You can divide by 2 if you want, or you can just leave it alone. So let's just leave it alone just for now. Well, now you're going to do the same thing for the next pieces. At x equals +1, these two pieces still need to connect together. So 2 plus 3A plus C. And then on the last one, like, don't panic because there's no X. It just means there's no X. So it just stays as 4. And now you've got the same type of thing. You have an A and a C in there. So just leave the A and the C on the left, swing the 2 over to the right. So you have 3A plus C is equal to 2. Okay, so now what? So that's where the calculus stops. Now it's just algebra to finish it. So what would you do? How would you solve that for A and solve it for C? Because now it's something that you learned in algebra 1.
So you have two equations, so solve them as a system.
Yeah. Which means you can use what two methods? One method starts with
Substitution
a
or
P.
elimination.
Yeah, substitution or elimination. It's your choice. Way back in algebra 1, they were pretty specific about which way to do it. It's not that way in calculus. You can choose your favorites. So you can use substitution, you can use elimination. Either way, and you're still going to get the same answer. So what do you guys want to do?
Elimination.
Elimination? Okay. How would you do it?
Well, it seems like you could add 2 times the second equation to the first equation to eliminate the C variable.
So take this equation, multiply it by 2.
Right. Right. Yeah.
Okay. Okay, so 3 times 2 is usually 6. That's a 2. 2 times 2 is usually 4. So your C's are gone. You have 8A is equal to 6. And A looks like it's 3/4. So now you have one answer. So you have the A. How would you get the C?
Plug it in.
Where?
Well, you could plug in the A to whichever equation you wanted, whichever one's easier. I think the first one was, I don't know. I mean, either one.
Like back to the original function?
Oh, I meant into one of those 2 equations that we just solved as a system.
Okay, yeah. Yeah, don't go all the way back up to where the x's are. Go back to either 2A minus 2C equals 2, 3A plus C equals 2. Either one, just plug it in and see what happens. So did you say you wanted the first one?
Sure.
Okay, yeah, it's like, it doesn't matter. You just got to pick one. Okay. So 2 times 3/4, that is 3/2. Swing over to 3/2. So what's 2 minus 3/2?
A half.
And now to get C by itself, we're going to multiply both sides by a -1/2. That way you don't have to divide a fraction by something. So the -1/2 cancels out the -2. So C is equal to -1/4. Easy peasy. So if you actually plug in the 3/4 and the -4 in for these A's and C's, and then graphed it, the graph would be doing something like that. Like each piece would connect together. There wouldn't be any holes, vertical asymptotes, anything that would destroy your discontinuity. Okay, so let's see, we've looked at limits with the graph, continuity. Number 7. Let's look at limits with a function. Oops. So let's take the limit as x approaches 0. Of 1 over x plus 1. Actually, let's make it 1 over x plus 2. So whenever you see a limit like this, like what is your goal? Like what do you want to have happen? Or what would you like to have happen?
Well, if you saw a limit like that, you would want to be able to plug the x value into the equation to calculate the limit, right?
Yeah, like you really, really want to plug in this number, because if you can, then you're done and you have an answer. So this was nice because you can do that, and it would just come out to just a half. But sometimes you can't do that. So like if you try to plug in this 0 into this function, you end up with 0 over 0. And I don't, in my entire career, there are still calculus students who see 0 over 0 and answer one of 2 ways. They'll either say it's 1, so they go, oh, it's the same thing on the top and the bottom. Or they'll say it's 0. Neither answer are correct. And because it's a limit problem, the other answer that I'm going to see a lot, and I saw it a lot on the quiz, is they'll say, oh, it's D and E because you had a 0 on the bottom. Even though, I think I talked about this in the video. If you have a problem like this, like you're actually trying to evaluate using algebra, it is going to be rare that it's a D and E. If it's an algebra problem, that means you actually have to use algebra to get to a place to plug in this value. So if you're saying, hey, this is D and E, you better stop and make absolutely sure that it is. So if you can manipulate it, and go from there. But don't just, if you come out with 0 over 0 or 5 over 0 or whatever, if you have a 0 in that denominator, don't just, oh, D and E, you know, work with it first and see what happens. It's like, what could you do with this?
You could factor out an X.
Yeah. And then your X's cancel out. And now you're left with X minus 1 over X minus 4. And can you plug in that 0 now?
Yeah.
Yeah. Now you just get to an answer of 1/4, which is way different than does not exist. So just be careful of these kind of problems. Like, don't just default it to D and E, you know, work with it and see if you can do anything. Now, sometimes it might be a little deceptive. Like you could have a problem like that. The limit as X approaches 0, just 1 over X. Well, if you plug in the 0, that is undefined, but you can't do anything. Like you can't manipulate this function whatsoever. Like there's nothing to factor out. There's no conjugate to use. There's no trig identity to just throw in there. So if you can't evaluate it by plugging in that number, what do you do? Other than skipping the problem and or crying about it.
You gotta draw it.
You gotta draw it. But what if you don't know what the graph looks like?
Table of values.
Yep, then you have to use the table. And since you're not allowed to use calculators, a table is going to be rather difficult to use. So I don't think I would default to that. So you're going to want to kind of default to the graph. Now, I'm not expecting you to graph something crazy. Like the basic parent functions, those are the kind of graphs that we're kind of looking for. It's like 1 over X is one of them. The trig functions, ln of X, e to the X, polynomials, like you got to know how to graph those. But I'm not going to give you something like, you know, ln of X over e to the X minus 1 and expect you to know how to graph that. Like, don't worry about graphing that type of a thing. This one, yes. So 1 over X, what does that look like?
Thank you. I'm on a Zoom call, yeah.
There's a vertical asymptote in the middle.
Okay, yeah, right.
There's on the bottom left quadrant, there's a curve going down like that. And then on the right side, on the top right, there's one going to the right from the top.
Yeah. All right, so there's your function. So now you've got something to work with. So now you're kind of going back to what we did in the first part of the review. So now you're tracing both sides as x approaches 0, and they're going in opposite directions. So now you have visually confirmed that it is a D and E. So this would be the only type of thing or situation where you're going to have a D and E's if you can't manipulate the function, but you can draw it, and the graph itself is going to visually tell you, hey, it's D and E. Okay, let's try this one. The limit as x approaches 0 from the right of root x. So a lot of people get stuck on that little thing up there, that little plus sign or minus sign sometimes. And when they see that, they automatically think that the rules are now totally different and nothing that they've done before applies. Is that true?
Nah.
No.
No. So whether it's a two-sided limit or a one-sided, your goal is still the same. You still want to be able to plug that number into the function. If you can, plug it in and you're done. If you can't, you got to manipulate it or graph it and see what happens. Okay, so can you plug 0 in for this x?
Yeah.
Yeah. And what's the square root of 0?
0.
0. I see that all the time in calculus as well. Just some of the basic math kind of gets lost a little. So yes, the square root of 0 is 0. What kind of numbers do you not want inside of a square root?
The negative kind.
A negative. Okay. There it is. I'm going to take this from the study guide, just because I know the problem will work the way I want it to. So the limit as x approaches 3 of the square root of x plus 1 minus 2 all over x minus 3. So there was a similar one to this on the first quiz. And I think at least a third, if not more, said this was D and E because they plugged in the 3 and it came out as 0 in that denominator. And then they just moved on. So again, if that happens to you, don't do it. Try to do something with this or graph it and see if it really is D and E. And I can tell you that if you try to graph it, that's going to be pretty difficult. So I don't think I would start there. Instead, you need to know how to manipulate it. So how do you manipulate this thing? There's a real specific trick.
The conjugate.
Yeah. Use the conjugate. And is it of the top or the bottom?
The top.
The top. The thing that has the square root in it, that's the conjugate you want. So the conjugate Like what would the conjugate be of this?
Root x plus 1 plus 2.
Yeah. So to get the conjugate, you just take the sign that's in the middle, like between the square root and the number. Just take that sign and switch it. So the minus becomes a plus, or if it was a plus in the beginning, that it would be a minus over there. And then you also multiply to the bottom. And why is that important? Like, why are you not just allowed to do it to the top? So why do you need to multiply to both places?
Well, you're not doing legal math if you just multiply an equation by something on the top. If you multiply on the bottom too, then you're multiplying by 1.
Yeah. Otherwise, yeah, he's right. You're doing something that's not allowed in the math world. It would be kind of nice in real life, because then you could tell your bank that, well, if I multiply my bank account by 100, that's the same thing, right? And they're going to go, no. So yeah, you have to multiply the same thing to the top and the bottom. So you're multiplying by 1. So the nice thing about the conjugate is that when you start to FOIL the top, the middle terms will always cancel out. So you don't have to worry about them. You just have to multiply the firsts together. It's like the square roots. So root x plus 1 times root x plus 1 is just magically x plus 1. And then the backs, you have -2 and 2. That becomes -4. Now the denominator, like you can FOIL that if you really, really want to, but you really, really don't. Because you're trying to get this x minus 3 to cancel out. So if you FOIL it, you're just going to have to factor it back. And you just wasted that time and you've gone in a circle. So for denominators, just kind of leave them factored out. So simplify your numerator to x minus 3. The x minus 3 is now cancel. And this is where another common mistake happens. Some people forget that when the entire numerator disappears, it doesn't mean that the fraction is gone. So if the entire numerator cancels out, then the numerator is now 1. And you're still over root x plus 1 plus 2. And what some people do is they leave the 1 out, and so now they don't have a fraction anymore. So now you can finally plug in the 3. Okay, so let's do it. 3 plus 1 is
Four
square root of 4.
is 2.
2 plus 2,
4.
4. And the 1 on top is still 1, so 1 over 4. Okay, any questions on this one that we just did? Okay. Let's see. Pretty sure it was in section 2.3. It was we towards I think the middle of it. We covered special limits. There's 3 of them technically, but we really only went over the first 2. And they're special limits because if you actually plugged in 0 into the function, you'd end up with 0 over 0, but the answer was not undefined or D&E. It was like 1 or 0. So do you remember what they were?
1 is sine x over x, and that's
Yeah.
equal to 1.
Yep. And what was the second one? Anybody know?
Wasn't it cosine minus 1?
What if it was 1 minus cosine?
Hey, that looks a little familiar. That's 0, right? Yeah.
Yep. And they both are.
Whoops. Yeah.
So it doesn't matter if it's 1 minus cosine or cosine minus 1. They're still both going to equal 0. So why is that? Like, why, if you switch the order, do you still get the same result? Because this is the one that was in the notes, but this one would still work.
Is because it cosine that equals 1. Is that why? Oh wait, no.
Because cosine is a special function.
It's just special.
You can factor out
Cosine,
-1.
cosine of 0 just equals 1.
Yeah,
But it's
that's what I
not
was.
because, but we're not plugging in the value. Because if we did, then you'd have 0 on the top and 0 on the bottom, which is technically bad. So it's not because of that.
Oh,
It's an algebra move.
So if you factor out a -1,
Yeah,
you get that.
he's right. If you pull off a negative from this, the signs would flip. So now, oops, the signs would flip. So now you've got the 1 minus cosine over x, which is 0, and the negative is still there, but -0 is still just 0. So that's why you can go in either order, because -0 is just 0. All right, now for the first one, what if the fraction was upside down? Does that still equal 1? Or does the sign have to always be on top?
Well, if the first one equals 1, then maybe you could call that 1 over 1. So then if you reverse, if you take the inverse of that other, the reciprocal, then maybe that's also 1 over 1.
Yeah, that is exactly right. If a fraction equals 1, its reciprocal will also equal 1. So whether it's this way or this way, like it doesn't, you don't care. It's still going to equal 1. Okay. So when you've got trig functions involved, sometimes you just have to get creative to try and get either this first limit or the second one to kind of pop out. Sometimes both, because if you can, then it'll take, it usually takes care of like the bad part, and then you can deal with the rest of it. So one of the problems in the book looked like this one. I'm not going to do the exact same one. I'll switch the numbers. So it was like sine of 7x all over sine of 4x. And you had to evaluate it. So you can't plug in the 0 because what's sine of 0? Sine of 0 is,
That 0.
that is 0. So you can't have 0 over 0 with these. So when that happens, you're trying to make these special limits come out. So particularly this first one, since it's the one that has sine in it. So what you're going to do is you're going to try to force either of these or both of them to show up. And let me backtrack a little bit first. In order to use any of these special limits up here, what has to be true about the angle and the denominator?
They have to be equal.
They have to be equal. They have to match up. So if they're not, if they're different, even in the slightest, then that limit doesn't apply and you got to figure something else out. So if you just had like sine of 7x, like what do you want to be underneath of it so that you can use this limit?
Also 7x.
Also 7x.
This is one of those really tricky ones, huh?
Mm-hmm. Okay. All right, so what I'm going to do is I'm going to split the signs apart so that the sine of 7x is by itself in one fraction, and then the sine of 4x is by itself in another fraction. And then we're going to do exactly what we stated before. We want the angle and the denominator, or the angle in the numerator, to match. So again, what do you want down here underneath this sine of 7x?
7x.
7x. Okay. And for the second fraction, in order to use that special limit, what do you want on top?
4x.
4x. So are you allowed to do this? Can you just put whatever you want in there?
I wish. No.
So what are you allowed to do?
Well, you can multiply by 1, so maybe you should also multiply those by their by like 1 over 4x and then 7x over 1.
Okay. So when you put something in the numerator and something in the denominator, they're supposed to also match. So we're a little bit off. And we're only off by the 4 and the 7. You have the x's there. Like you have an x on top and an x underneath, so that's okay. It's just their coefficients that they're lacking. So take care of that, we're gonna have a third little fraction. So if you put a 4 on top, where else do you have to put a 4?
On the bottom.
On the bottom. And if you put a 7 on the bottom, where else do you have to put a 7?
On the top. Can you explain one more time why we are not including the X's here?
Sure, because you already have one on top and one underneath. Because it's multiplication, it's not like 4 plus X. And let's just say you forgot and you just put them in there anyway. Like 7X
Oh,
plus X. What
okay.
happens to these two X's? They
Okay.
just cancel off, right? So that's essentially what you're doing.
Okay, thank you.
Yeah. And now you've pretty much got it because the sine of 7X over 7X, that goes to 1. 4X over sine of 4X, that also goes to 1. There's no X to worry about in this green fraction. So you have 1 times 7/4. And most of the time that is 7/4. I think the one of the homework was like sine of 2X over sine of 3X. I think they had 2's and 3's in there. So that's how they got their answer. I don't remember the order. So their answer was either 2/3 or 3/2. But that's how you do it. So there you go.
Could you explain one more time why you multiply it over 7x over 4x?
Because you need the exact same thing on top as you do the bottom, right?
Mm-hmm.
So you put a 7 down here, right? On the bottom. Did you put a 7 on the bottom?
Yeah.
Yeah. So where else do you have to put a 7?
On the top.
On the top.
Okay.
So yeah, you put a 7 down here. So you got to also put a 7 on the top somewhere. So I just do it in like in some little fraction. You can put it here, here, or wherever, as long as it's on top somewhere. Now you also put a 4 on the top, which tells you that you have to put a 4 where else. On the bottom. So put a 4 somewhere on the bottom, either there, or in another little fraction. Now the X's, you already have an X on top and an X underneath, so you don't need any more X's. If you put them in there, it's okay. So let's say you went 7X over 4X. It's not wrong, but what do you notice about this X and this X? What can you do with them?
You can cancel them out.
You can cancel them out. So they're going to cancel out even if you stick them in there. So you can save yourself a little bit of hassle and not worry about them. Or if you stick them in there, it's okay because they should eventually go away. And just leave you with the 7 over the 4. Another way to look at it too is these green things up here. If you did 4X times 7, what is that?
28x.
28X. What's 7X times 4?
28x.
28x.
Did you put the same thing on top as you did underneath? Like, are they
Yeah.
both 28X? Yeah. Okay, let's see. I'm trying to think of other non-calc stuff to know. Oh, yeah. Let's see, what's inverse sine of a half?
$90.
No,
Is that 30 degrees or like pi over 6?
pi over 6. Yeah, in calculus, your default mode should be your radians, unless otherwise stated. Okay, what's inverse sine of 1?
Pi over 2.
Yeah, that's the one that's the 90 degrees or the pi over 2. What about inverse sine of negative 1/2?
Negative pi over 6.
That is negative pi over 6. Okay, so you got to know like your inverse trig functions and how to evaluate them. So inverse sine, inverse cosine, inverse tangent. Let's see what is, oh, here's a big one. What's ln of 1?
0.
That is 0. So yeah, don't leave it as ln of 1. That will always simplify down to just 0. What about ln of e squared?
2.
That is 2. Because the ln and the e cancel out. And why do they cancel out?
The way I think about it is ln is log base e. And if you have log base e of e, then the base and that x term or whatever it is equal each other, which means they cancel out. So like, according to the formulas that we learned, the answer is going to be that exponent.
Yeah, but why do they cancel? Like what you said is correct, but all you did was just change or just describe what ln actually is. But why do they cancel?
Is E like the inverse of ln?
Yeah, e and ln are inverses of each other. So that's why when the base of the ln or the log matches the base of the exponential, they'll cancel out because they're inverses.
Got it. Thanks.
Yeah. Ah. Okay, what if you had sine squared plus cosine squared? What is that equal?
1.
That's 1. What kind of identity is this called?
Pythagorean.
Yep, Pythagorean identity. Okay. What if you had secant squared minus 1?
Cosine? Oh no, not cosine. Cosecant?
Nope.
Is that tangent squared?
That's tangent squared. So it's another Pythagorean identity, but it's a little out of order, which is okay because the Pythagorean identity, like you can move things around. So like, for example, if you had 1 minus cosine squared, that's not a direct Pythagorean identity either, but you can still use it and get what as an answer.
Sine squared.
Sine squared. Because all you've done is taken this equation here, you've just moved the cosine squared over to the right side. What about 2 sine theta cosine theta? Anybody remember what that equals? You hear people
Oh,
clicking on
I
their
don't know.
mouse. That is sine of 2 theta. And you can go the other direction too. So if you add sine of 2 theta, you can rewrite it as 2 sine theta cosine theta. So this is why, like in your trig class or pre-calculus class, like you went over those identities, which a lot of people do not like, and they're like, why are we doing this? Well, this is why, because when you get to calculus, like you don't have to do the proofs, but you have to know like what you can change them into, and how to recognize them. So that's why you do all those proofs, so that when you get here, you can just switch them out. Okay, so you got to know your inverse trig stuff. You got to know your like your Pythagorean identities and like this double angle identity. You got to remember stuff about like logarithms and exponential functions. So like if, just in case you needed it, like if you just add ln of x, what does that look like as far as a graph?
I mean, it looks like, I think, I guess would you call it an increasing? It looks like an increasing exponential function that hits the x-axis at one.
Yeah. So yeah, it hits it at 1 because ln of 1 is 0. So that's your x-intercept. And there's a vertical asymptote right on the y-axis, or right at y equals 0. So this would be one of those parent graphs to know. 1 over x, square root of x, x squared, x to the third. Absolute value of x, what's that look like?
V shape.
Yep.
So really, it would be a good idea to kind of try to memorize, I guess, the shapes of some of these so that you can like move more quickly through quizzes and tests without having to like stop and think.
Yes. So that's why, at least in this district, for like American River, Folsom, Cosumnes, and Sac City, that's why they don't want you to just jump from your trig class to calculus. So you have to go trig and then pre-calculus and then calculus, is because they're trying to fill in all of these holes that you might have in your math knowledge that you're expected to know by the time you get to calculus. Because it
Definitely.
helps. 'Cause-
Yeah. You know, I was surprised to see, yeah, like that we needed to know.
Wait,
those
wait, wait,
trig
wait,
identities.
wait. Make sure you're not talking about the second quiz.
I'm talking about, I'm just talking about I guess the first quiz.
Hmm.
But even just the first notes is what I'm getting at, is
Oh.
that, you know, we kind of had to, there was trig there, and I was like, oh, you know, I didn't really know that we would need to do trig, and so that was
Yeah.
surprising.
Yeah, and not just some trig, but like just about all of it. So you got to know the graphs, how the functions work, how to evaluate them, how to evaluate the inverse functions, how to work with identities. Yeah, because so like section 3.1, just for an example, that is the stepping stone from limits into derivatives, and every function has a derivative, including the trig functions, the inverse trig functions, exponentials, logarithms, polynomials, like any type of function you can think of, you can find its derivative, including combinations. So all those functions that you guys looked at in pre-calculus, they come back into calculus, which is one of the reasons why it's hard. Like the calculus concepts are people can kind of understand and get through. The hard part is the algebra and the previous stuff from your other classes that you just got to remember how to do. Algebra being a big component of that.
Hey,
So-
at least all that stuff we didn't learn it for nothing then.
Yeah. So that's why calculus is hard. Pre-calculus, it's hard because there's just so much material. Calculus is hard is because you got to take all of that material and use it. All right, we have about 40 minutes. So what questions do you guys have for me?
I have a specific question coming from somebody on that Discord server, and they were wondering if we can do a problem such like numbers 33 or 37 on the 3.1 homework. And those were the problems where we had like, we had to find a derivative of a function that, a tangent line that was parallel to a given line. So they were saying 33 or 37 from 3.1.
We could, I'd rather not. Hint, hint.
Gotcha. I think we can also just kind of discuss those problems on the Discord server. I know some people were able to do those problems, so it may not be a big deal if we don't go over it, but yeah.
It shouldn't be.
Roger.
Maybe for the next exam. Okay, anybody else have something they want to go over? Or a question on something? Not all at once.
For the infinite limits, are we only doing it graphically?
Doing it graphically.
Or I think the book had it said like imagine it's 1 over a really small positive number. And you kind of do it like that.
Are you talking like if you're given the function versus
Yeah.
given the graph?
Like you're given the equation and then it said
So something like the limit as x approaches, we'll just say 0 from, do you want the left or the right?
the right.
The right. Okay, so the limit is x approaches 0 from the right of, we'll just say x plus 1 over x, like that.
Okay, yeah.
So what I would do is just evaluate each term. So like you can plug the 0 in for this first x, so I would go ahead and do it. And then plus, but you can't plug it into the second term, the 1 over x. So for that one, I would go off of the graph. I think what you described is like where x, where they said plug in like a really small positive number. That's kind of trying to approach it like with a table. Which I personally, I would much rather not do, because that table is really tedious. And you don't have a calculator, so it could get pretty tough. So I would just go off the graph of this. So that's, what we drew earlier, just this one. And if you're going off the graph, just, draw the graph. If it's a problem where you have to show your work, just draw the graph so there's some justification as to how you got your answer. So as you approach 0 from the right, it's going straight up to, where's it going?
Positive infinity.
Positive infinity. And so now that you've evaluated every term, then you can just add everything up, and 0 plus infinity is just infinity. So that's how I would do it. So there you go. Is this kind of like what you were talking about, or am I way off?
Yeah, that's helpful.
Okay. Okay, what else do you guys have?
I have kind of a follow-up question.
Sure.
So in one lesson, it said that the cases of DNE, one of the cases was unbounded behavior, where something just continuously goes up and you answer that as DNE, but sometimes we answer that as infinity or negative infinity. Where's the difference?
So in section 2.2, that's where, so you first learn about limits and what to do and when DNE was. So they said if it goes off to infinity or negative infinity, that's a DNE. But in 2.5, they changed it. So it's still like if something goes to infinity, technically the limit is not existing, but you're saying how it doesn't exist. So if something's going, if a limit goes off to infinity or negative infinity, that's what you're going to put. So the classification in 2.5 overrides the classification in 2.2.
Okay,
That makes sense.
yeah, that makes sense.
Yeah, they just didn't want to do the two sections together because I think they thought it was just too much at once, which is probably true. But yeah, if a limit goes off to infinity or negative infinity, that's how you want to put it.
So just to be clear on that one, just leave it as infinity.
Yep. Yeah, if you
Okay.
put DNE, that would get marked wrong. So DNE, you only put if the right side does not agree with the left side. Otherwise, there should be a numerical answer or infinity or negative infinity.
Professor.
Mhm.
So on assessment questions like a test or a quiz, sometimes we have to show our own work and then submit a PDF.
Yes.
For those types of questions, is partial credit given? Like if you're doing so if you're like doing a delta epsilon proof or something and you mess up the
Mhm.
algebra, you could
Yeah.
still get like maybe even most of the points. I don't know.
Yeah, depending on the severity of the error. So like if it's like an arithmetic type thing, then like you'd maybe lose a point. So instead of 5 points, you might get 4. If it's severe, so like you tell me that 2 divided by 0 is 2, or you do some off the wall error, and I cannot think of one. Like you might get dinged a little bit harder. So instead of 5 points, you might get 1, depending on what you do. Or if you only do half the problem, then you're probably only going to get like half the points.
Right. I mean, if you did like something over 0, then you might just be skipping the whole problem. So that makes sense.
Uh-huh.
Thank you.
Yeah. So let's say I don't like this type of a problem. Like the limit is as x approaches 1 of x plus 1. What's the answer to this?
2, right?
2. So for this type of problem, like it's pretty easy, and I know you can do it in your head. That would be all the work you would have to really do.
Right, which is
Right.
none. Mhm.
Yeah, like if it was like the limit as x approaches 2 of x minus 2 all over x squared minus 4. You need to show some work with this. You need to be able, if it's a algebra thing that you're doing, you got to be able to justify your answer. So if you just have a numerical value for that, you're not really showing your work.
Right. Right.
And it's especially important, like if you get it wrong, there's no work in there for me to grade. So that would, I couldn't award you partial credit. So if you want partial credit for stuff, other than something like this, then you got to show your work. Even if it's a step, at least give me something to grade. So I can give you points. The free response, how I look at it is I'm trying to figure out ways where I can give you points. I'm not trying to figure out ways where I can take them away.
Good. Yeah. So so for this, then you would show the factoring of the denominator. You don't have to show like how you did it, but yeah, you would show the factoring, show the cancel, and then plug in X and then answer. It's like 3 steps or something.
Yeah. Or even if you just went, you wrote the limit, you factored it, and then you canceled it, and then you plugged it in. That's okay too, but at least you showed me like how you got from here to here. There was some step where some magic happened. Otherwise, you're expecting me to just take it on faith that you knew exactly where this came from if you just went just straight to an answer.
Totally. Yeah.
So yeah, those free response questions, that's where your partial credit's going to come in. And point wise, trying to remember how it's broken down for this one. The partial credit, the free response questions on the exams, point wise, that's pretty close to about half of the points themselves. So like the multiple choice and the fill in the blank, that would be about half maybe, or a little over.
Yeah.
And then the free response would make up the rest.
Yeah. I
Usually,
remember
not every time. But.
Yeah. I remember on the first quiz, which everybody has taken at this point.
Yeah.
I was showing like the multiplication of like 16 times 16 just to make sure that I knew, what that big number was. And like, I probably didn't have to show all of that work. So I guess I also need to kind of get used to knowing how much work to show, because I basically ran out of time on that one. Yeah.
All right, let's see, what else can I answer?
So for the epsilon delta problems, are we
Yeah.
gonna have to know how to do the ones that have like the interval? I think it was like 37 for 2.2. Or
Oh,
could
where
we
it gave you like
go?
the quadratic one.
I don't have my notes in front of me because I'm at work, but I just remember that one, like you had to do like an interval and pick points, and you had to work it out a little bit different.
I would say no.
Okay.
I mean, I can, if you really want me to, I can go back and put one on there.
No, I went over it with, I'm in the math 80 class. And so I went over that with Chris,
Olson?
the tutor.
Oh, Chris, okay.
And he said that it probably wouldn't be on there, but I don't know. I was just wondering because that one's still like, we went over it for probably a good half an hour and it still like barely made sense.
Yeah. So like other study tips, just in addition to like just actually doing the problems so you can prove to yourself that you can do them. The definitions, make sure you understand what they're saying. Not that you've memorized the definition, but like, do you understand what's in there? Particularly the stuff on continuity. The delta epsilon, that's a definition too, but that's only used in the proofs. But the continuity definition, like, do you understand what those 3 criteria mean? Or can you only repeat it? So like when it says the FFC is defined, do you know what that means? Or do you just know that, oh, it says FFC is defined? And that will be true for, the other exams as well. Like, do you understand the definitions? Do you understand what they're saying? Do you understand the parts of them? Can you break them down and apply them. So if I give you a situation and say, oh, does this definition apply to this? Like, could you actually do it? Or do you only know what the definition says and that's it? So those types of questions would be more like your critical thinking ones. And that's something I'm really interested to know, is if you can actually think versus regurgitate material. So you might see questions where you have to come up with your own situation, or come up with your own graph, or come up with your own function where this definition might apply, or where this definition wouldn't hold. That type of thing. It's like, I can't get too specific with this exam because I don't want to give away any exam questions. Just make sure you understand what they're saying. And some people just panic, like, oh my gosh. But I'm not asking like 30 questions on critical thinking questions. Like, there's going to be some, but not a ton of them. Actually, I have a question for you guys, because I didn't go over it. Do you have any questions on the intermediate value theorem?
Oh, that's actually good. I actually had a confusion on one of the intermediate value theorem questions.
Sure.
Give me 1 sec to pull it up. Sorry.
That's okay. Like from the notes or from the homework?
I'm trying to remember. It may have been the homework. It was either the homework or it was the study guide. I think it was the homework. Give me just 1 sec.
It probably wasn't the study guide. The study guide just has you state it, which means if I ask you to state it, that means I expect you to know it and to be able to use it.
Yeah, it must have been from the homework. I'll be able to find it. Some other people were confused also. So
there are a couple of ways it could go from the homework questions. If it's like, use the intermediate value theorem to show that there could be a zero in the interval. Or the other way they asked it was, verify that the theorem applies and then find the value of C guaranteed by the theorem.
Right. So this was number 101 on the homework. Which homework was that? It was
2.4.
Yeah,
Or-
whichever one had that stuff. Let me see. It is. Here it is. Yeah, 101 from homework. Yeah, 2.4 exactly. And so basically the this was asking. Sorry, you kind of caught me off guard. So yes, so this gave us a function, a polynomial, a third order polynomial, and an interval, and it says f of c equals 4. See if the IVT applies, and then find the value of c guaranteed. And the process, I think people are okay with, and I was okay with like the IVT itself, but it was just the algebra and solving
it
to find the value of c. I did like 20 synthetic divisions, and I only found 1 0, and maybe we could just kind of go through it.
What was the function?
So the function is f of x equals x cubed minus x squared plus x minus 2.
And what was the function value they wanted you to set it equal to?
Well, we have f of c equals 4.
Okay.
Right. And the interval is 0, 3.
Okay, so here's your function. You set it equal to 4, and then we got to solve it. And then just make sure that your solutions are in here. Okay, so move over
Yes.
the 4. So the question was, okay, how do I solve that?
Right. And so I use the rational rational zero theorem. And
Okay.
then did synthetic division. Is that a good approach?
Yes, because that's the only approach. The other one you could, that would have been really nice. Whenever you have 4 terms in here like this, factoring by grouping is always a great way to go.
Yeah.
But on this one, that didn't work.
Right.
So your only method is to do what you just said, the rational roots theorem, and so use the synthetic division.
Yeah.
And so was that 8, or was that come out as 2?
Yeah. I mean, I can save you time. Yeah. Don't do 20 of them. It's just 2. And then there's no multiplicity. So then you're left with still a trinomial, which I
It's
then,
quadratic,
sorry.
but it's quadratic, right?
Yeah. Well, so like basically I got, this here, a 0 and a factor, which would be x minus 2, right? X minus 2. And then you're left with, isn't that x squared or c squared plus c minus or plus 3, right?
Yeah.
And so I couldn't factor that trinomial there
Right.
anymore. I put it into the quadratic and I got, it would have been an imaginary number, I guess. So that, I guess, told me that there's no other zeros. And I was like, okay, I guess it must be 2.
Yep.
But I was left feeling a little bit confused. So.
Okay. So I'm not sure, confused about what, because everything you said was right.
Okay.
So yeah, if this quadratic doesn't factor, then you're right. You have to use the quadratic formula or completing the square. But you'd have to use the quadratic formula to figure out where the zeros are.
Yeah.
And yeah, you are right. It comes out as imaginary. So this doesn't yield a solution. It's only coming from the C minus 2. And that's it.
So there you go. So if we were given a gentler, easier problem, then we might have gotten several solutions, and then I guess we would choose the one that's inside the interval, right?
Yeah.
Okay, then I guess that's fine. I was just confused that that I ended up having that thing that I couldn't factor, and I was like, I guess the only thing I can see to do here is say 2. So yeah, okay.
Yeah. So yeah, if some of it doesn't give you a solution, then it just doesn't give you a solution. Because you probably wouldn't have even thought that something was wrong if it was like this. You would have said, oh, C equals 2, because I can't solve that.
Totally. Yeah. Okay. Yeah.
So yeah, if a part's not solvable, then it's just not solvable, and then just go off the rest of it.
Yeah. Yeah. I ended up plugging 2 back in and it was right. So, okay, good.
So now a bunch of eyes just got really, really big because of this whole process right here. And you're going, oh my gosh, I do not remember synthetic division. I do not usually give a synthetic division problem in calculus. I would in a pre-calc class because that's where you teach it. It's something that comes up every so often. Like you'll probably see it once in this class here. You might see it again. And then you might see it like 2 more times in calculus 2, and then maybe 2 more times in calculus 3. So it is a rare method that to me is rare enough that I'm not going to throw it onto an exam. Homework, that's one thing, because it's like, oh yeah, it helps kind of jog your memory a little bit, but I'm not going to give you a synthetic division problem on the exam,
Generous. Thank you.
unless you really want one. But I'd rather not. So if you do have like 4 terms, it should be factorable without having to do this. Because a few of you are going, I have never seen that before in my life, which might be true. Your pre-cal teacher might have skipped it. They shouldn't have. So if you've never seen this, then you should be okay. And your whole calculus career is not in jeopardy. All right, any last minute questions? So we get down to the wire.
Oh, do you have like an ETA on when these latest quizzes will be graded, or like are we waiting for a certain time to pass or anything?
It's like usually I do try to kind of grade them as they come in. I just can't reveal answers until they're all in. Except like, doesn't Canvas kind of give you like a pre-score? Right, like you kind of, you know, like your score based off of the multiple choice, the true and false, the fill in the blank.
Yes, but that was I think it was only like 4 points out of 20. That's fine. That's fine. I was just wondering because I think my quiz was graded like super quickly last weekend, and I was just wondering.
Okay. So I usually try to grade them as they come in. But certain events have prohibited me from doing that. But I can't reveal anything until all the quizzes have been in. So I can't, like, if you got something wrong, I can't tell you like why or or what the answer should be until after it's due.
Right. Well, hopefully we covered everything that we needed to in this review session then. Thanks.
Yeah.
Could you go over 3C from the quiz?
From the first quiz?
Yeah.
3C. Do you know what that was? Oh, I know what it was. It was the limit with the radical in it, wasn't it?
Yeah.
Do you remember what yours was?
Yeah, I have it right here. So it was the limit as x approaches 4, and then it was 16 minus root x plus 252 over 4 minus x.
Do you remember what you put as an answer?
Oh, I didn't get to it because I ran out of time.
Okay.
Yeah.
All right, class, how should we evaluate this? We did one like this earlier. So what did we do? How did we tackle it?
If you're asking everybody, we use that conjugate. We multiply by the conjugate.
Mhm. So even if it's, if the radical is first or if the radical is second like this, it doesn't matter. Just change the sign that's in between the number and the radical itself. So it'd be 16 plus your x plus 252. And that's to the top and the bottom. So we'll leave the denominator alone. One, because it would be a lot of work to FOIL it. And two, if you FOIL it, you're just gonna have to factor it right back so you can get the 4 minus x to cancel. Okay, so what is 16 times 16?
256.
256. And then minus root x plus 252 times itself is just x plus 252. Now you do have to be careful because that minus sign is going to distribute across that quantity. So really what you have on top is 256 minus x minus 252. And so if you simplify the top, whoops, I went down my limit notation. 4 minus x is on top, that'll cancel the 4 minus x on the bottom. Now you can plug in the 4. So let's do the arithmetic out loud. What's 4 plus 252?
256.
256. What's the square root of 256?
Oh, can't do that with that calculator.
Yeah,
Just
I just did it earlier.
16.
16. 16 plus 16.
32.
32.
Yeah, I was so nervous when I saw that square root of 256. I was freaking out
So you realize something?
pretty much.
Yeah. Like, oh. Okay, so for whoever asked that, did that make sense?
Yeah, that helps. Thank you.
Okay. You're welcome. All right, you have about 2.5 minutes. Okay. All right, well, hearing that there's no other questions, I guess we will adjourn for the day.
Thank you, Professor.
Oh, you're welcome.
Thank
guys asked some
you.
good questions.
Thank you.
You're welcome. Okay, so if you still have questions or if you think of something else, just shoot me an email and I'll be able to hopefully send you a replies for when you actually need an answer. um, so hopefully soon. But yeah, if you still have a question, just let me know. All right, good luck on the exam. And I'll talk to you guys later.
Thank you.
You're
Thank you.
welcome.